My name is Matthew Graham, and this is the last module in a series of 6 on databases. In previous modules, we've talked quite extensively about relational databases, the data model behind it, and the supporting technologies. I would maintain that this is because a lot of big data analytics can still be done on relational databases. However, there comes a point where a relational database is not sufficient for the type of problem that you're trying to deal with. Alex Zalay has said that anything beyond 300 terabytes is generally difficult when you're trying to do any form of data management, and relational database systems are tuned for small but frequent read-write transactions or large batch transactions with unfrequent write accesses. This tends to mean that they're scalable in terms of your dataset size or read-write concurrency. You can always spread the database onto multiple servers and clusters of services, distributed clusters of services in some cases, if the types of problems that you're wanting to deal with are still that you have small but frequent read-write transactions or large batch transactions. Number of data, amount of data, greater number of users doesn't really matter. Problem comes, however, when you move outside of that sweet spot, when you've actually got more reads happening than the database system can actually cope with, or more writes are being put onto the data. If you have too many joins going on because of the way that you've structured your database, even if you've normalized it, well, particularly if you've normalized it, actually, because that encourages joins, that can cause performance issues. You find that the queries begin to become slower. Also, if you are doing a lot of complex queries on the database, making use of a lot of stored procedures and possibly even views, where there's a lot of server-side computation required to support a particular query, then you can find that you get performance problems with a relational database. Fortunately, as we've seen in Module 2, when we talked about different types of data models, there are other ways of representing your data, and therefore different technological solutions which may be more appropriate for the type of problem that you're facing. Different types of data store that you may consider if you have a scaling problem with your data. There's a particular combination of solutions called QServe. This is an open source implementation that's come out of the LSST project. This uses MySQL as the fundamental data store at the back end, so it's still relational, still makes use of SQL as the query language, maintains acidity, and it uses an Xroot D layer on top, and doesn't share anything between individual instances of the servers which are supporting this. But this is a scalable relational solution designed for the petascale data volumes that LSST is envisaging. So this may be a good solution for you if you're facing that sort of problem. Moving away from the relational databases, there's the SciDB project. This is a column-oriented database. Column-oriented databases essentially are a 90-degree rotation of a relational database. It's the column which is the important thing, not the row. And instead of it using tables as its first-order data type for storing, it's based around the idea of numerical arrays. So this is a very good database for large amounts of numerical data, large amounts of scientific data. It has substantial industry backing, so I would recommend going to scidb.org to look at this if you are interested in it. It also maintains ACID, so it's broadly the same types of transactions as a relational databases we're using. Moving away from the relational model even further, in recent years there's been a movement called the NoSQL movement, and the idea is that they want to reject many of the precepts of relational databases and move to something that is far more performant, essentially a glorified hash table with that particular data structure. So these are largely optimized key value stores, where the type of data object that's being stored is a key and a value. So large lookup tables. They're not ACID, but they are very good for web scale solutions. The Hadoop project has produced a number of these, and certainly they came out of the Google project with MapReduce and stuff like that as supporting technology. A more recent development is the so-called new SQL movement. The idea here is to take the performance that you get from no SQL, but you want to have a relational model behind it with SQL, because that is what we're used to from relational databases, and a lot of people have technologies and applications which are built on that type of model. New SQL, examples are HStore or Google Spanner technology examples. Another possible example is NuoDB, which is a new SQL type graph-based system, but for doing that sort of modeling. And the new SQL systems make use of what's called a sharding middle layer for performance. Sharding is a type of partitioning where you have multiple horizontal partitions from the same schema. So the idea is to try and optimize particular data access, but making use of horizontal partitioning, but multiple schema versions. So those are particular types of data store you might want to look at if you've got scalability issues with your particular big data problem. In terms of alternatives to relational data stores that are more based on some of the other data models we talked about, it may be that you're actually working with a large amount of XML data. XML is the W3 standard, the worldwide consortium standard for markup language for structured data. If you've ever seen a data file which has got angle brackets in it, that's probably an XML file. It employs a hierarchical data model. That's the type of tree structure, if you remember. And there are a number of supporting technologies for working with XML data. XPath is a standard for allowing you to point to particular elements or attributes or the values of those within an XML document, within an XML file. XSLT, so-called style sheets, are standard for converting that XML angular format to other formats, whether it's HTML or comma-separated variable or some other alternate data structure that you want. And XQuery is a standard for querying XML documents in the same way that SQL is a standard for querying relational tables. There are a number of databases which are specifically designed for working solely with XML data. These are the so-called native XML databases. Exist is the most popular open source one. There are also a number of relational databases which have XML support. MySQL and SQL Server, for example, both have added support for XML-specific data types in their most recent versions. An example of an XML document is given here. You can see that the indentation is denoting particular hierarchical levels. We have element names inside the angle brackets. We also have attributes inside the angle brackets. This is a record describing a catalog, an astronomical catalog that may exist in a directory service somewhere. And you may have multiple examples of such things, and you actually want to work with them in that format. It may be because of the hierarchy that there's not a natural translation into the requisite relational data structures in a relational database that you would require to represent this type of information, so using a native XML database may be more performant. This is an example of XQuery. This is an equivalent to the select statement. This is in XQuery, this is called flower, this type of construction. And you can see that you're defining some namespaces. They're just defining areas of concern. and then you're defining particular variables to be the results of XPath statements pointing to particular elements within inside an XML document, and then there's a for loop with a where statement in it. The predicate argument of that where statement is exactly the same type of idea as the predicate that you have in a SQL statement. There's an ordering, and then you can return the result, and one of the powers of XQuery is that you can actually format the result that's returned. In this case, it would format the result in a particular type of XML document, a new XML structure that we would be interested in working with. And this is an example of XQuery. Another way of working with data is in the form of RDF, Resource Description Framework, that I mentioned in the first module. This is a W3C standard for data interchange. It makes use of the associative data model, and if you've heard of the semantic web, it's the main underpinning of the semantic web, the so-called web of data, next generation internet, Web 2.0, that sort of thing. The basic idea is that you represent all data in the form of subject, predicate, object triplets. For example, Pluto is a dwarf planet. Again, there are a number of supporting technologies. Sparkle is the query language for RDF data. RDFS is a standard for modeling RDF data in the same way that you have database schemas for modeling relational data. SCOS is a standard for representing controlled vocabularies. This gets more into the idea of knowledge management, the upper echelons of the data information knowledge wisdom pyramid. So if you have a controlled vocabulary that you're using in your particular domain, SCOS allows you to represent that in a formal machine processable format that you can then program against. And ultimately, OWL is for representing concept schemes, so-called ontologies, which represent full formal encapsulations of domain knowledge in a particular area. Triple stores are the names given to databases for storing RDF data. You also find that there are some relational databases out there which have Sparkle interfaces so that they can participate in distributed queries over RDF data. This is the so-called linked data or open linked data that a lot of big data sources like DBpedia, which is a version of Wikipedia, have interfaces exposing their data through Sparkle, and so you can issue queries against those. This is an example of Sparkle. The top part of the slide shows, again, you're defining a prefix, and then you're selecting, using a select statement. In Sparkle, the question mark denotes the variables that you're interested in, so you're just selecting, you want the capital and the country, where what we are asking for here is to find the capitals of countries which are in Europe. And we would be hitting a triple store containing a set of triples. Sample data in the lower half of the slide shows the sort of triples that we would have. So you can see that the where statement in the Sparkle example is a join of a number of types of statement. We're looking for cities which have a name. The city is designated as the capital of a country which is in the continent of Europe, in this particular case. We have a schema which defines a set of predicates. The predicates in this case would be city name is capital of, country name is in continent. So our sample data, this example would return the first one, that Berlin is the capital of Germany. The answer we would get back is Berlin, Germany. But the other data that is in the database would be required to check the types of queries that we're interested in making. Finally, I'd like to talk about ontology-driven databases. This is where data is modeled at both the syntactic and the conceptual level. So this is making use of RDF and OWL. You have your data represented in RDF, and it is structured, but you're also representing the domain knowledge behind the data in terms of the ontology, capturing the concepts and the relationships between those concepts and their properties, and making use of that in a formal way. And an ontology-driven database employs this formally expressed domain knowledge, and it allows you to do consistency checks not only against syntactic consistencies to make sure that data is in the right data type, associated with the right data structures, but also for conceptual checks that particular definitions of objects and the sorts of properties that they may want to have are not inconsistent. So an example is you may have an ontology which is describing something like a star, and it may say that a star has a certain set of properties. It may be that data in your database, in your triple store, is defining a star to have, there may be a particular star which has got a measured property which is inconsistent with that, and by doing a consistency check against the domain knowledge, you would be able to identify that inconsistency in your database. This use of domain knowledge also allows you to do logical inferencing, so that you can do first-order logic, apply first-order logic to your database, and identify new pieces of information which are logically consistent, or the logical follow-on from the facts that you have in your database. So you may be able to identify new properties based on a set number of specified properties which are all consistent within the domain knowledge. Examples of this sort of thing are where you have possibly a database of protein information and you have an ontology which is describing particular associations between metabolic phenomena and protein phenomena, and you can infer particular metabolic phenomena from the protein phenomena that are specified in the ontology, and in your database you do not have that information yet specified, but you can infer it to generate these new facts which are consistent with the knowledge base that you're using. This sort of ontology-driven database facilitates smart applications. It means that I can write a query against the database which would then infer information from the database consistent with the knowledge base that I'm using and give me answers back that I'm interested in. An example is that I may have a database of zebrafish anatomical images, and they're labeled up with the particular thing that they are displaying, but by using an anatomy infrastructure, an anatomy ontology, I could infer what substructures of those anatomical structures are, or superstructures are, and so I might ask, for example, all images which display the hindbrain, but then it may also return to me in my search things related to the central nervous system, or to the brain in itself, or to individual parts of the hindbrain, or possibly to structures or cell structures that develop into the hindbrain, making use of the ontology to do the logical inferencing of that type of information, even though that's not necessarily specified in the database itself. Because it's in the ontology, we can infer it on the data in the database for the sake of applications. So with that, I will end this series of 6 modules on databases. I hope you find it useful. Thank you.